we will introduce my end-to and trajectory planning work. GuideFlow. Currently, autonomous driving has become an emerging technology in the field of intelligent transportation and is expected to reduce traffic accidents caused by human driving. End-to-end autonomous driving aims to receive multimodal sensor inputs and directly perform trajectory planning based on them. In the process, other modules handle intermediate tasks such as object detection, mapping, and motion prediction. Current end-to-end methods based on trajectory planning can be divided into two series. The first series uses imitation learning, directly applying MSE loss supervision between the predicted multimodal trajectories and a single ground truth trajectory. The problem with this approach is that the model often faces the risk of mode collapse, and the trajectories are typically the average of multiple styles, for example, transfuser. The other series uses generative methods for trajectory generation, such as diffusion drive and GuideFlow. However, these methods employ implicit generation, like supervision over the generation process, and still rely on imitation learning as the optimization strategy. Furthermore, they lack diverse style guidance, making it difficult to ensure trajectory diversity. In contrast, our method explicitly supervises the flow matching process, thereby avoiding the problem of mode collapse. Furthermore, it leverages multiple guidance signals for classifier-free guided generation, such as driving commands, target points, and trajectory anchors. In addition, we quantify the level of trajectory aggressiveness and use it as a style guide for trajectory generation. In addition, to constrain the generation, we propose three methods. The first is CVF, which uses velocity field composition for constraint. We first use a scorer to obtain a constraint satisfying anchor. Then compute the difference between this anchor and the initial Gaussian sample to obtain a correction velocity field. This correction velocity field is then added to the model predicted velocity field to constrain the model generation. The second module is CF, where we directly replace the generative sample with a constraint setting anchor during the generation process and continue sampling, which effectively corrects the flow state. The third module, ARF, employs an energy model to optimize the trajectory after flow matching. Following the idea of energy matching, we use a single model to simultaneously model both the flow matching model and the energy model. Through these three approaches, we enhance the constrainability, controllability of trajectory generation. Our method significantly outperforms other imitation learning methods as well as other generative methods, such as diffusion drive, on the NavSim dataset. In addition, additional ablation experiments demonstrate the effectiveness of our three constraint approaches. Interestingly, when using the RAS module, which encourages aggressive trajectory driving, the model's EP score increases, demonstrating the effectiveness of our guidance approach. We provide some visualizations. It can be observed that our trajectories, while satisfying the constraints, exhibit styles different from the ground truth trajectories, which indicates that we do not rely on imitation learning. Furthermore, we demonstrate our model's ability to switch trajectory styles. In comparison with diffusion drive, GuideFlow shows safer planning. Thanks.